Okay, let's do a short Simulink tutorial where we build a closed loop block diagram in Simulink that resembles this and simulate the closed loop response and plot it. And let's do, say, a set point change. So this part of the block diagram is what nature gives us. This tells us how the disturbance D contributes to the controlled variable y. This transfer function tells us how the manipulated variable u contributes to the controlled variable y. So because both the disturbance and manipulated variable come together and both influence y, they're added together here. And then y is fed back to this comparator and compared to a set point, which computes the error. This comparator computes the error. And then the error is fed to the controller. So this is the P controller. And then the P controller is what we add to the process as engineers to manipulate U. And so this tells the manipulated variable what it should do. And so let's see how this response looks like when there's an input change in the set point. Okay, so first let's fire up Simulink. So I'll just make a directory for putting my files. So I'll call this P control demo. And cd, I'll change this directory and fire up MATLAB. Okay, and let's start from scratch. And you can see where you are with PWD. And so this is the path in which my present working directory is. And whenever I run a Simulink file, I'll look in this folder for my Simulink file. Okay, so first let's wire up the Simulink diagram. Simulink. Type that in, that should bring up Simulink. And we will ambitiously start with a blank model. And first, we will put in the two transfer functions for the process, the intrinsic process dynamics. And so this library browser is what I always use to search for blocks. And let's look for an LTI system that stands for linear time invariant. And this can contain our transfer function that describes how the disturbance and manipulated variable influence the process, influence the control variable. Okay. And so let's let this one be GP. So this is how the manipulated variable influences the process. We said it's 3.2 over 4s plus 1. And so this stands for transfer function. And then these are two polynomials that you put here. So 3.2 and then 4s plus 1. So this is the coefficient in the denominator in front of the s. This is the coefficient in front of 1. And the numerator is just a constant, so we don't need to make it an array, but it could be an array. Okay, and just to show you what this does, so if I go here and paste it there, you can kind of see what the transfer function looks like. It's 3.2 over 4s plus 1. And so yeah, you could make this higher order like this. Okay, and that's how you would make a higher order. Okay, so that's GP, and then we can copy and paste that to make GC, or GD, which is how the disturbance variable influences the process. So there's GD. Okay, and this transfer function is 1 over 2s plus 1. Make that a 1, make that a 2. All right, and then these two, what comes out of these transfer functions, they're added together. So let's search for a sum, because we're going to sum these two signals together, and that's what's going to make y, right? Okay, and so this is sort of awkward. The plus sign is down here, but I kind of want it up here, so I can feed it in this way. So you can double-click that and change can basically rotate this. And so I permuted the plus and this vertical line, which corresponds to the output. And so now the pluses are in the right direction. Let me delete that one. Okay. And let me connect that one. Yeah, okay. And then these come together and determine what y is. Let's make these a nice color. I'll make them green for the intrinsic process dynamics. So this is like a tree, so this is like nature. This is nature, and as engineers, we can't really help this except through the design of the process. And then what comes out of here is the controlled variable. And we want to save that to the workspace because we're interested in how it behaves with different inputs. And so this basically takes the output of this sum block and saves it as a variable, and I'll call this y. And its format is a time series, and I'll show you what a time series is later once we run it. But basically it contains a list of times and a list of corresponding y values. It's a data structure in MATLAB, and we'll call this y. Okay, and we'll also be considering step inputs in the disturbance eventually, but you can really feed in anything here, but we'll look at steps. So we'll look at step inputs, so step. So here's a step, and this is going to be the disturbance variable d. Okay, and so it's really d star. And if you double click that, this tells you the time in which a step occurs, then the initial and final value. So I'll just make this 0 for now because I told you in the beginning we'd be looking at set point changes. So I'll make that 0. So in reality, this here is sort of redundant, but later, if you do consider disturbance, then you'll need to turn this on. Okay, and then we have a controller which feeds into which determines what the manipulated variable is, which is fed into this transfer function. So let's make the controller. So this is GC, and the controller can also be represented by a transfer function. And we'll make this a different color because this is what we, as engineers, add to the process to harness it, to control it. Yeah, and we said that we are going to look at a P controller, and the transfer function for a P controller is just a gain. And so let's say we want the gain to be 3. Then we can just do this, and that's a pure gain of 3. And so this is a P controller. And the controller needs to take as input the error. And so we need another sum block that computes the error given the set point and the actual y value. Well, this is oriented correctly. So here's the error that'll come out of here. And then into this, and we'll make a step change in the set point. Again, you can imagine any sort of input coming in here that is a set point, but we're going to consider a step. So this would be y set point star. Yeah, and we'll feed that in there. And then this should be a minus sign, right? Because we want to subtract the actual y value from the set point. There we go. Okay, and then we basically want to take this and feed it back here. It's easier if you click here first. Okay, there. And voila, we have a very nice feedback control loop. Let's double click our set point, and we can actually simulate changes in the set point now. And let's make this happen at t equals 2. And let's let the final value be 1. And this here, 10, tells you how long you want the simulation to run for. And so 10 units of time sounds fine, given that time constants are 2 and 4. So 10 is a reasonably long time. And so you could just hit play right here. And my computer made a sound indicating that it ran successfully. And then if you go into your MATLAB workspace, you'll see what popped up in the variable as a variable in the workspace is this variable y. And that is the output of your Simulink. And that's because of this toWorkspace block here that we have. So we told the Simulink diagram to output this to our workspace, and voila, here it is. And you can see it's this complicated time series object, but you can access its attributes. So if you do y.time, then it gives you an array of times, and it goes to 10, just like we told it to. And then these are the corresponding y values. And so what we really want is to make a plot of these, right? And so you could type all the commands in here, or you could make a script so that you can run a series of commands and save it for later. So, for example, we could plot the response. So if you bring up a figure panel, and then I want to plot the times versus the data. And so the x label here will be time t, and the y label will be y star t. So it's in deviation form, right? So let's run that and see what it looks like. And it's asking us to name the .m file, which is the script we're writing. So I just, let's say, run p control, save, and now it should be running. Oh, and we have a nice plot here. And you can see that at time 2 is when the set point change occurred, and then the controller, through the manipulator variable, causes the control variable to increase and approach the set point, but not quite reach our desired set point of 1 because it's p control, and there is a steady state offset there. Okay, so there are a few things I don't like about this plot. One, the font size is a little small, and the lines aren't very thick, and so you can customize that. ... to go to the next line. And so line width, I like it to be 3 for a nice thick line. And to change the font size, we can say, I think it's set GCA font size 25. Yeah, there. GCA means get current access. And now when you maximize it, it looks very nice. Okay, so that looks nice. All right, and I also like to plot what happens when there's no control. And so if there's no control, then basically you put it in a set point change and there's nothing listening to you, right? So there's no action taken on manipulated variable. And so no control would be just y equals 0, right? And so you can plot that here too. So we can plot the same times, and then we can plot zeros 0.0, but I believe that it should want an array. So let me try this. I know in Python yeah, okay. So we have to plot this array against another array, not against a float. And so you can make an array of zeros with zeros, like 0 is 3. Should give you an array. So let's do zeros length of, so 3, 1 should be an array of 1s, yeah. So let's do zeros length of y.time, comma 1. Yeah, and so that would be a column vector of zeros, and they will have the same number of zeros as y.times. Yeah, and so this should work. Okay, it's y.time, not times. Yeah, and here we go. So now we have a plot of just 0 here. And what happened is it deleted the other plot that we put out, right? So it sort of erased the last plot and overwrote it with this. But we want both of them to show up at once. And to do that, we put hold on, and that will allow both of these to plot at once. So again, let's make this a bit thicker. And let's make its color black. Yeah, there. And this is what would happen if there were no control. Okay. And let's also draw what the set point is, 1, just to really emphasize that the set point is not being reached. And so we really want the same thing. The set point is 1, and so instead of zeros here, we put 1s, and we'll make it a different color. Let's say red. Okay, and we can actually make it dash too, so you can do that with line style, and that means dashed. Now, one thing that's problematic here is there's 3 different colors, and so we can really be clear of which color corresponds to which situation, and we can make a legend. So this command, legend, and then you put, so basically the name of this series of data here, which is p control, and then the name of this data series, this corresponds to no control, and then the next series is the set point. Okay, yeah, and see now they are nicely labeled as to what is what. And so basically p control never allows you to reach your set point, and you have a steady state offset change, steady state offset error. And if you increase KC, the offset error will be diminished and you'll get a faster response, but practically that could lead to instability. Okay, and so at this point it might be nice to also find out what the controller action is. And so this here is the output of the controller, right? And we can actually spit that out into the workspace as well and see exactly what the controller is doing in order to coax the system to maintain the set point. And so this is our to_workspace variable here. Let me copy that because I want to make another variable output to the workspace. And so this is u. This is u. So basically, let me put it here. And so this basically records exactly what is coming out of the controller, and it will throw it into our workspace. Okay, let's move this up a bit so that there's room. There we go. Okay, and so really, we'll highlight these because these are what we are throwing into our workspace. Okay, so these are what we're throwing in our workspace, and these are the inputs. Okay, so maybe we'll make those red or something. Yeah, okay, so this is what we're throwing in our workspace. And we'd also like to know what the controller action is. Okay. All right, and so I would like to plot both the response and the controller action in the same plot. And to do that, we can use subplots. And subplots basically allows you to make an n by n plot. And so here I want m to be 2 for 2 rows and 1 for 1 column. And then the next argument tells me, okay, which subplot do I want to draw on now? And so I want to draw on the first one. And if I hit play, basically the same thing will come up, but now it's in the upper half of the signal, or of the plot. But I want to draw another plot here that has the manipulated variable. And so for that, I call the second argument because I want to draw on the second one. And now instead of plotting y, I want to plot the p action, which is basically u. And let's give it a different color. Let's say blue. And then the x label here is still time t. And the y label is now the manipulated variable that the controller spits out. And let me set the font here. Okay, and when I run this, I'm going to get an error. And the error is going to be because u is not defined. So you see it's not in the workspace. So I hit run, nothing, it will get an error. And that's because I need to rerun my Simulink block diagram. And so to avoid mistakes like that, so mistakes like going into Simulink block diagram and changing the parameter but then forgetting to rerun it, you can go up here and say sim is in simulate and then the name of your Simulink file. So let me save my Simulink file. So let me save it as pcontrol. .slx, yeah. And so now I can say sim pcontrol and it'll actually run that Simulink block diagram for me. And then we'll see u pop up in the workspace and the plot is made nicely. There we go. And so now we see not only the controller, or not only what the control variable does, but the controller output, so the p action. And you can see that at first, when you first make that set point change, the error is enormous. And that's when p action, which is proportional to the error, of course, is largest. And then as y comes up towards the set point, the error diminishes, and therefore p action does as well. And because there's always a steady state offset here, the P action is non-zero even at steady state. Okay, and so to sort of complete this, let's give these plots a nice title. So the title of this is P control. And then let's make the title down below P action, because we're really looking at what the controller action is. Yeah, there. And we could save the plot like right here if you click save. Yeah, that looks quite nice. Okay, so hopefully that was helpful.